part of it, lead kindly light. And of course, the second part of it is more specific, more technical, which talks about spectroscopy and the periodic table. So why did I choose the first part of the title? So that's what I'm trying to explain here. In fact, I have been fascinated by one poem by Cardinal Newman, which he wrote in way back in 1833. It starts as lead kindly light amid the encircling gloom, lead thou me on. And that's what actually we would be looking at throughout this presentation of how light, or rather the wavelength discrimination of light, which we call as spectroscopy, how it has been able to lead us to come up with a proper periodic table. That's the whole idea with which light has been brought into the periodic table and or the spectroscopy aspect of it. In fact, more fascinating is the Kannada version of it. I don't know how many of you would have even come across this particular translation. I shouldn't say translation. ಅನುವಾದಕ್ಕಿಂತ ಮೂಲ ಭಾವಾರ್ಥ ಚೆನ್ನಾಗಿ ಬಂದಿರುವಂಥ ಕನ್ನಡದ ಇಂಗ್ಲಿಷ್ ಗೀತೆಗಳಿಂದ ಒಂದು ಕವನಗುಚ್ಛದಿಂದ ಆರಿಸ್ಕೊಂಡಿದ್ದು ಕನ್ನಡದ ಕಣ್ವ ಬಿ ಎಂ ಶ್ರೀ ಅವರು ಕರುಣಾಳು ಬಾಬೆಳಕೆ. I think you would have heard about this particular song. This is quite an inspiring one, and how actually light is equated to godliness is what this entire poem is about. Let me not take you to the literature world, but rather continue on the periodic table, which is what the topic that we should be discussing today. And in about 40 or 45 minutes, I will be starting with a very brief introduction, and then go into something that I call as a story mode. And especially today, I have chosen 3 main stories of how to talk about, how to correlate the spectroscopic aspects of light and the periodic table, or how spectroscopy helped the periodic table to be put on a firmer footing. That's what we are going to look at when we talk about these 3 stories. So the first one is about the gas burner and the elements, and especially it will talk about it will involve a person for whom the network analysis, and I'm certain that a large number of you would be very familiar with the network analysis, or at least would have been taught the network analysis, something that the teachers call as the Kirchhoff network analysis. This is for electrical networks, and how to analyze that is something that a particular person had put. And for him, for that particular person, it was a child's play, and we all struggle to do that sometimes, at least the network analysis. And for this particular person, it was a pretty easy job, and he was quite involved in this story number 1 on gas burner and the elements. And the next story is about the lazy but the noble lots. And there is an Indian connection that I'm going to talk about, however tangential it is to the periodic table at this juncture of the noble lots. And then we are going to look at probably the last of the stories to be described today, of a man who could claim saying that I laid the basis for the modern periodic table, and a tragic end this person goes through, and it's a loss to science itself. So I would want to call it as science's loss to patriotism. And in principle, I can go on regaling n number of stories, but probably, as I have promised already, that I would be talking about only 3 stories, and I would come up with something that I would call as a postscript, or an outlook to the periodic table as it stands today. Give me a minute, please. I'm sorry. So let's begin with a bit of introduction, as I said. So this is my favorite thing when I talk about especially periodic table, or the elements, or how the chemists treat materials in their laboratory. And by training, I'm a physicist, but I have a good number of very good chemists, outstanding ones. But this is my way of pulling their leg. So I start talking about the distribution of different elements at different stages. And I start with the most macroscopic, most global scale of all that one can think about, our universe itself. And look at the kind of elements that we are talking about here. Hydrogen occupies a very large percentage of the material that's available in our universe. It takes about 74%, a very large chunk, 3/4 of it almost. And then comes helium, so 24%. So if you add up the two, that makes it about 98%. 98% of the matter that is available in the universe is nothing but hydrogen and helium, only two elements. And then comes our favorite life-giving oxygen, which is about 1.4%. So where are we now? Already 99.4. The rest of the elements that we know today, if they are naturally occurring, then of course, as we will see later, there are also elements which are not available in the nature but can be prepared in the lab. That's what I mean by naturally occurring elements. So they make up only 0.6% of the entire matter that's available in the universe. And the chemists have to struggle getting the maximum out of this 0.6% that's available in the universe. Then we come down in the level, right? Directly from the universe, we come to Earth's crust. And now the scenario changes. No more hydrogen dominating the scenario, but it is the oxygen, of course, because it is the life giver. So therefore, oxygen dominates. Oxygen dominates because it's available as not only oxygen in air, but also in two other chemicals, water and of course carbon dioxide. Both are important for life on Earth, and oxygen is an important component of both these chemicals, and that's how the percentage of oxygen is pretty high, about 46%. And then of course silicon, which makes a large percentage, 28%. And then you have a whole lot of materials starting from aluminum, iron, calcium, sodium, magnesium, all with decreasing contribution to the total mass of the Earth's crust. That's how we look at the distribution of elements when we are talking about Earth's crust. And then we come to life. Okay? Here, as I've already mentioned, oxygen dominates the scenario. Then comes carbon, hydrogen, and decreasing contributions by other materials. So in order to appreciate, I have taken this periodic table as represented in the hyperlink that I have already shown over there, chem.libtex.org. And I urge you to go through some of these links that I would be showing in the presentation. They give you far more information, far more detailed information than what I can describe today in the duration that's available to me. So, but what I wanted you to appreciate is, as it stands today, there are about 118 elements, and this is showing only 115. 118, the candidature of the 119th one is being considered for approval, and so therefore we still talk about 118 elements today. And out of that, what you see is the purple one and the green one are the elements that are essential for us. The purple ones are the most essential, and suggested to be essential for humans are the green ones. Then look at it. A large number of elements that we are talking about are not absolutely required for life to be sustained on Earth. But still, of course, with all the fervor that a chemist actually goes forward and then uses a large number of these elements in order to come up with a variety of either the materials or the products that we are quite familiar today, and each of them plays an important role. But what I wanted to stress is nature could do with a small subset of this entire periodic table. About 30 and odd elements is all it uses, whereas man actually boasts saying that we can actually employ each of the 118 elements that we have described, that we have discovered for one or the other reason. This is what actually the difference between something, a man-made world, and the world as nature had made it. This actually takes us to a completely different kind of thinking about how periodic table should be looked at, and whether we can actually move towards how the nature has created the world and reduce the number of elements that we are going to use up in order to come up with whatever useful products that we want. This topic is actually not directly related to the discovery of the periodic table, so I want to leave it at that, but I want you to appreciate another aspect of it before I leave this topic. I want you to look at the bulk elements that are present in, let's take the example of a human being weighing about 70 kgs, let's say. Oxygen constitutes about 44 kgs, carbon about 12.6, hydrogen, nitrogen, and sulfur in the numbers that I have shown over there. These are the bulk elements. And then come the macro minerals like calcium, phosphorus, potassium, chlorine, sodium, and magnesium. Look at the unit. I had used kilograms for the bulk element, whereas I'm using macro minerals for the gram as the unit for the macro minerals. Then come what we call as the trace elements, and now the unit is actually in milligrams. So what I have progressed towards is something like the ratio is something like 1 million between bulk elements and the trace elements, and this is how the progress actually takes place when you are comparing different elements that are employed that are present in a human being. In order to make it even more appealing, what I have done is I have put there those quantities in a graphical representation. And what I have done on the left, the vertical axis is a logarithmic axis. I'm sure that you all appreciate a logarithmic axis, a logarithmic representation of something which varies over a wide range, starting from something like 44 kgs to something that is only a few micrograms. So that kind of a variation you can see of how most of the elements that we are talking about, which is in the blue region, they're available only in trace quantities, whereas the rest within the bulk taking a large portion of the mass of the human being itself. So this is the way that nature has worked, that it wants to employ only a few elements in order to come up with something that is sustainable, and that's probably is a big lesson for us. With that kind of a philosophical note, I will actually start with the main presentation that I wanted to do. So who doesn't love fireworks? Come Deepavali, we all enjoy it in various ways. And of course, especially those which actually blow up into eye-appealing colors over the sky are something that we all appreciate, whether we are little kids or grown-ups or oldies like me. We all appreciate that beautiful colors and the kind of patterns that they can generate. And now for this kind of a firework was actually known, the earliest documentation for that kind of a thing of how to arrive at a particular color in order to generate it from fireworks was something that an information that was known to mankind, and especially the Chinese, as far back as about 14th century. They talk about recipes of what kind of chemicals should be put in order to arrive at a particular color in the fireworks, whether it could be a military signal or whether it is for entertainment or any such application of how to have different chemicals. So therefore, it is like establishing in a very naive way the correlation between the color of the firework that you want and the kind of chemical that you will be employing in order to generate that particular color. Of course, in the modern world, we are far more developed about this correlation between the two. So if I want a particular red today, I can order it depending on the kind of strontium or a lithium salt that I employ. I can get a particular hue of red, or if I change it to calcium salts, for example, end up with orange. And if it were to be any other thing that I have mentioned here, for example, if it were to be a barium compound, I end up with green. Whereas if it is of strontium plus copper, I can end up with purple. So therefore, now this is a very well documented kind of thing, and that's how even the firework manufacturers have benefited significantly from the chemistry that is involved in this correlation between color and the kind of element that we should be having in those fireworks. So this actually was something like the basis for the first story that we are going to talk about today, which I have called as the gas burner and the element. So this is something, an object that all of us, all students of science, are certainly familiar with. What is this? This is a something that the teacher has told us is a Bunsen burner, right? This is a Bunsen burner, and actually the Bunsen part of it is coming from Robert Bunsen, who actually invented, I should say, this kind of a burner way back in about 1855 or so. So why did he have to invent it? Bunsen was a professor, and he was invited by the University of Heidelberg to set up a chemistry lab. And it so happened that during those times in Heidelberg, uh, the government had just then switched over to a new kind of lighting, which is actually gas based. And they also insisted upon, for any heating applications, people should be using only gas as the source. This was a new economy that the government was coming up, and so they were urging, forcing, impressing upon people that they should be employing in households certainly, and also, as it happened in Bunsen's case, in laboratories also, they should be employing uh, gases for heating as well as for lighting purposes. So it so happened that Bunsen was interested in this problem of studying the color of the light emitted when different elements, chemical elements, were heated to a certain temperature. That was his goal. But his main problem, and his observation, of course, was that whenever he used the gas that was available to him, there used to be a sooty flame. Soot is the black smoke that comes out. The sooty flame, and with that sooty flame, the flame used to be always burning yellow because of the presence of carbon. And so therefore, the problem now for Bunsen was that if he wants to differentiate the presence of different elements contained in something, depending on the kind of the color of the flame, it would be nearly impossible, because the color from the incandescence of the carbon atoms, which burn with a very bright incandescent yellow, it would be difficult to check the different colors for the different elements, because the incandescence from the carbon would dominate, and so therefore what you end up is the yellow flame from carbon, and so therefore it would be difficult to differentiate what comes with the different elements. So therefore there was a need for a burner, he thought, at least there was a need for a burner, a device that would produce a flame with very little soot. So after much discussion with an engineer in their university, his name is Disaga, they come up with a design wherein their aim was to maximize the temperature and minimize luminosity in the system. So you need to achieve two things simultaneously. You have to maximize the temperature, but at the same time minimize the luminosity of the system. So therefore, they come up with this design, the engineer as well as Bunsen himself, Robert Bunsen himself. So they designed this. Probably, if you Google this, you will be getting more information on the exact design of the Bunsen burner. But the most important part is what is shown over here, then, which controls the amount of oxygen available to the system. So the solution that Bunsen had come up with, which Disaga could implement and create a new burner, was to control the amount of oxygen supplied to the flame. And if every one of you who have worked in a chemistry lab using a Bunsen burner would clearly know that the teacher would prefer you to have flame number 4 rather than flame number 1 when you want to employ it to check which element that you have in a particular system. So therefore, the incandescent flame is something that you should do away with, and finally end up with that blue flame that I have shown on the extreme right. This is also the time at which the flame has the highest temperature that's possible, and incandescence or luminosity is at its minimum. If you say that Robert Bunsen's contribution was only this Bunsen burner, but you would be probably doing injustice to him. he was also responsible for the discovery of two important elements, cesium and rubidium. And of course, the important part is also that the flame test is a procedure that he came up with. But I'm mentioning this especially cesium and rubidium for a very simple reason. It talks about, it's a big lesson for all researchers like us of the kind of patience one should have when one is doing laboratory work. Why do I say that? In order to get something like 17 grams of cesium, Bunsen had to distill something like 40 tons of water. How much is a ton? Something like 1,000 kgs, right? So something like 40,000 kgs of water he had to distill in order to end up with 17 grams of cesium. That's the kind of patience one should have in order to get good results in research. So there is no substitute for being patient while you are doing research. That's what I want to emphasize. Bunsen was not alone in this establishing the correlation between the color of the flame and the element that's going to get into the periodic table that we'll be talking very shortly. So another person, his name is Gustav Robert Kirchhoff. You would be familiar with this name. Physics teachers would have taught you in electrical analysis classes about Kirchhoff analysis. It is the same Kirchhoff that I am talking about. In fact, for Kirchhoff, this was not something that was taught in the university, but rather as a student, he was made to come up with a seminar with an important topic that one could appreciate. So that's when actually for a student seminar, Kirchhoff came up with this beautiful, profound analysis of how to do network analysis of different electrical components. And in fact, network analysis is one of the major fields where he has contributed, but there are two others. And as you would see here, I have put the three, that's Kirchhoff's photograph. And I have put the three topics where he contributed significantly. The circuit loss is something that we are not going to discuss today. The second one also is something that we are not going to discuss today, is the thermochemistry contributions. But it is the last one, the three laws of spectroscopy that Kirchhoff contributed, which is actually laid the basis for what Bunsen and Kirchhoff came up with for the correlation between the element and the color of the flame that it emits. I have put in here the different colors of the flames and the kind of, for example, lithium gives you a very bright red, sodium gives you yellow. Look at this, all are halides of these elements. Potassium gives you a very light violetish purple, and cesium so on. So therefore, depending on the element that you have, or depending on the halogen content, for example, then you can actually change the kind of flame that you get when you subject the element to the periodic table. So this formed the basis for the two guys, Kirchhoff and Bunsen, to analyze this in great detail. And it is Kirchhoff who did a significant amount of analysis on this and then came up with three beautiful laws which actually stand today as Kirchhoff's laws of spectroscopy. I've stated here the first law. It says a luminous solid or a liquid or a dense gas. What do I mean by a dense gas? A gas under high pressure, you are calling dense gas. So it could be either a solid or a liquid or a gas under high pressure. It produces a continuous spectrum when exposed to a light source. That's what we mean by the first law. Of course, this object is a hot object. That's when it can emit a spectrum. So you should have a hot, that's what luminous means. A hot solid liquid or a high pressure gas produces a continuous spectrum. You can go from the VIB to the GAR kind of end, violet to the red end continuously without any break. The second law talks about significantly different aspect of the spectrum that comes. Now what you have done is take the same gas that you had earlier, but reduce its pressure significantly. It becomes a low density gas now. Since the pressure is low, the atoms that are present in this gas are farther apart now, but the gas is still hot. So therefore, we are talking about a low density gas which is hot. It produces now, instead of a continuous spectrum that we saw earlier, it produces an emission spectrum which is a line spectrum. Specific bright lines are present which are representative of the kind of chemical content that the gas contains. The third law is now what happens if you cool this low density gas. Whether the spectrum that you get is the same or not is the question. You get the same spectrum, but now instead of those lines being very bright, now they are dark lines on the background of a continuous spectrum. The continuous spectrum comes because you have a gas there, which is its chemical content is showing up, but then what you have is that the gas is now cool and has a very low density. So they are going to appear as dark absorption lines on the background of a continuous spectrum. This is his third law. In fact, all these features are used even today in something called a flame photometer, which the pharmaceutical people use significantly in order to understand the chemical content of the medicine that they prepare. So please remember all these, keep in mind all these three laws when we are going to talk about its application. So we are going to apply it to an astronomical situation, a situation that exists outside the Earth, for example. So what happens here is the type of spectrum depends on the temperature of the thin gas relative to the background temperature. When I'm talking about temperature, I'm talking about a relative temperature of the gas with respect to the temperature that it is present in. So if there is a thin gas cooler than its background, the gas is cooler than its background, and an example of that is you have the sun represented here, whose outer surface temperature is something like 6000 Kelvin. Let's say you have a gas which is at 5000 Kelvin. What you have are the absorption lines. We already talked about the the third law of how it gives an absorption spectrum. In fact, Fraunhofer had already discussed this some time ago, and Kirchhoff borrows from Fraunhofer analysis, Fraunhofer observations, and puts this on a firmer footing using the kind of laws that he had already generated. So if instead of this, if the gas is hotter than the background, which you can generate in the laboratory, you get emission lines, but their position is exactly at the same values of wavelength where you have the absorption lines in the first spectrum that I showed, where the gas is cooler than its background. So this is the way that Kirchhoff could actually establish that these two situations are identical actually, but depending on whether the gas is hotter or cooler than its background, you can end up with either an emission or an absorption spectrum, identical in their wavelengths. So he built a spectroscope based on this, and using this spectroscope, he invented, in collaboration with Bunsen, of course, most importantly, employing the new laws that they had discovered, they showed that the sun contains sodium. Please remember, this is about a century and a half, and that much was known about astronomy. And sitting here on Earth, somebody could actually detect the chemical content of an object as far as the sun itself. So this was a revelation for Kirchhoff, and actually this is how later it has been established in a similar kind of thing, that hydrogen is an important component of sun, and the same comparison of the absorption spectrum and the emission spectrum, people could prove the presence of different elements in astronomical objects. I would actually say spectroscopy is a very important component for astronomers even today. And so therefore, between Bunsen and Kirchhoff, they established a new kind of business for the astronomers. And I think astronomers should be thankful for these two guys for finding them jobs. With that, I move to The next story, I don't know how much time I have for Dr. Sidegoda. Could you confirm? We started, I think, about 7 minutes late.
Sir, okay, no problem, sir.
Okay. My clock says 28 minutes, so I think I should be having another 30 and odd minutes. Yeah. So I go to the second story, which I have labeled as the lazy but the noble lots. So this again I want to take in terms of the story actually like the narration of a drama. In fact, it happened almost like a drama, as you will see from my description in the next few slides. The two protagonists, the two main players of this drama are Sir William Ramsay and John Strutt, also known as Lord Raleigh. In fact, the duo got the first Nobel Prize to the British Isles way back in 1904. They got the first the first Brits to get the Nobel Prize. The pictures of those two guys I have put here. On the left, you will see Ramsay. On the right is Lord Raleigh. The story, I would, as I said, I want to describe in terms of a drama. And so therefore, this drama that I am talking about unveils due on the occasion of a lecture to the Royal Society that was being delivered by Lord Raleigh. The title of the talk was On the Composition of the Air. You should appreciate that people didn't understand way back in 1894, 19th April, that's the day of the lecture. They didn't understand much about the composition of the air, and people were doing very serious experiments in order to understand what is the composition of the air. In fact, this kind of an experimentation was going on almost for a century, as we will see in a very short while. So Raleigh's talk was based on a publication that he had put in Nature, a very venerated, highly rated journal called Nature. Even today, it's a high impact factor journal, as we call it in today's parlance, Nature. And he had published an article titled The Density of Nitrogen. And towards the end of the talk, concluding the talk, Raleigh quotes a sentence that he had put in the article, and I quote it here. I am much puzzled by some recent results as to the density of nitrogen and should be obliged. Look at the kind of wordings that one uses. Very humble people. Shall be obliged if any of your chemical readers can offer suggestions as to the cause. As for what? His puzzle is this: the discrepancy between the density of nitrogen made by chemical synthesis in the laboratory and the nitrogen that is isolated from the air by removing all other non-components. People already knew what air contained, at least a few components that they knew. So they knew how to take out those components using synthetic methods. So if you take out those components, what is left was nitrogen according to their analysis. And so Raleigh's puzzle was, if he compares the density, the mass density that I'm talking about, of the nitrogen obtained by isolating it from atmospheric air to the nitrogen that he was able to prepare in the laboratory by synthetic means, if he compares the two, there was a discrepancy. There was an error in the values of the two. So the difference between the two of values was quite small, something like 1 part in 1,000. If you say, if for example, he was not a careful experimenter, probably he would have pushed it under the carpet, saying that probably there is some error kind of thing. But look at this scientist. This is what actually makes good scientists. He says the difference that he talks about, 1 part in 1,000, is entirely outside the errors of experiment, because he was so confident that with the accuracy of his measurement, he says that this difference is really significant and not coming from the errors in my experiment. So this was the kind of puzzle that he had. And as a suggestion to what could be causing that was, Raleigh says, contamination by a lighter gas in the synthesized one. He makes some gas in the laboratory. Maybe there was a lighter gas impurity which was present in small amounts, and this was the reason why there is a discrepancy in the density between the two nitrogens, the one in the lab and one from the lab and one from the atmosphere. Ramsay would have just walked by to listen to Raleigh's talk, and he listens to this entire talk with rapt attention, and also is puzzled by the kind of observation made by Raleigh, and also his comment that there could be a contamination by a lighter gas in the synthesized one. But then Ramsay quips, he makes a comment saying that, Lord Raleigh, why couldn't it be the opposite? There could be a heavier impurity in the atmospheric one. This is not some just to pull the leg of the speaker, a kind of comment by Ramsay. In fact, he would have dwelt upon, he would have read a little bit about what Cavendish had published about a century ago, his observations. Ramsay would have read the notebooks of Cavendish, wherein he had made a very detailed kind of analysis of the atmospheric air, which he calls the fictitious air. So that's what Ramsay's that was the basis for Ramsay's observation of there could be a heavier impurity in the atmospheric one. So this kind of a question and a suggestion by a listener made the two people, Raleigh and Ramsay, forge a collaboration. Raleigh was a physicist, Ramsay a chemist. Intense collaborations. Act 2, Scene 2, I could call it, August 1894. Please remember the date of the lecture was April 1894, and the collaboration forges very well in August 1894. What happens? 4th of August, Ramsay isolates a new gas from the atmospheric air and informs Raleigh. What was the mode of information providing? It was not the day where they could actually, those were not the days where you could send an email or send a WhatsApp kind of message. Those were the days, 1894, end of 19th century that we are talking about. So they had to send it by regular post, the so-called snail mail. And so therefore, Ramsay writes to Raleigh saying that he has been able to isolate a new gas. 6th of August, 2 days later, Raleigh writes back to Ramsay. Look at the kind of wordings again. I too have isolated the gas, though in miserably small quantities. Please appreciate the point that Raleigh is a physicist and Ramsay is a chemist. When it comes to isolation of chemicals, there is no way you can beat a trained chemist. And Ramsay had to be a better person in this than Raleigh, and Raleigh appreciates that part. And so therefore, but he could also isolate this gas. So that's what the agreement was about. And so therefore, just a week later, they were so confident of the observation that they have got and the isolation of the new gas. On the 13th of August, they announce it to the Royal Society, saying that they have a new gas which they labeled. Actually, the label was not given by them. There was a chair when Ramsay gives the talk. The chair actually, I've forgotten his name. The chair actually was the one who suggested that they should call this gas as argon, or the Greek word for lazy. In Kannada, there is a saying, Sumana iddavananna brahmanu gellalaranta, which only means that if you don't react to a comment by a person, the person can't do much harm to you because you are not reacting at all. So therefore, the fight won't continue at all. So therefore, you can extend the same kind of an argument to this situation also. You should appreciate those were the days when people were identifying elements based on their chemical reactivity. And these were, as you would see later, these were noble gases, which means that they do not have any chemical reactivity, and that's why it was really impossible for people who were basing their arguments on chemical reactivity to identify this particular element. Of course, when you announce such important things, a breakthrough, there would be a lot of skeptics who don't believe you at all. And of course, in the case of Raleigh and Ramsay, the detractors, the people who didn't believe them, were not simple people. Mendeleev, the person actually who had already come up with a periodic table which was arranged on the basis of atomic weight, was putting his weight behind this argument, saying that both Raleigh and Ramsay must be talking nonsense. There cannot be something, a gas, an element that doesn't react at all. There is no element which doesn't have chemical reactivity. So they must be talking some nonsense, is what Mendeleev, Dewar, etc. argued. And so therefore, they were actually detractors. So if that happens to some of us, to some scientists, actually, we become very disappointed with the kind of thing, with the responses that we get from the other world. And so therefore, we could even give up research on that kind of thing. Not to Ramsay and Raleigh. In fact, they struggle hard. 5 months of intense research by Ramsay and company, in their entire team. They provide spectroscopic evidence using the kind of spectroscopic evidence that I've already talked about, established by Kirchhoff, and then they prove that actually there is indeed a new gas. And in 1895, Ramsay comes back to Royal Society, gives a beautiful lecture which was titled Argon, a new constituent of the atmosphere. In fact, the spectrum of argon I have put here, these are the kind of spectral lines that they could identify, and that didn't match with anything that was known till then. And so therefore they knew that they had a new gas, and it was taken from atmosphere. So therefore argon must be present in the atmosphere, was their powerful argument. Continuing on other noble elements apart from argon, which was first discovered by Ramsay and Raleigh, I continue the story about other noble gases. Of course, I have already told, Ramsay and Raleigh get their Nobel Prize for the noble gas that they invented. Please note the difference between the two. NOBEL is for the prize because it comes from Alfred Nobel, his name. NOBLE, we have given the name for noble elements which do not react with other materials so easily. So that's the difference that I'm trying to make. So other noble elements were also discovered, but this time there was an Indian connection, and also that this person is not a chemist, is not a physicist, but rather an astronomer. So you would be surprised, how could an astronomer discover a new element? So his name is Pierre Janssen, and his idea was to study the solar spectrum. He was using his solar spectrometer, and his idea was that in order to reduce the noise in the system, he should be studying the sun spectrum during a total solar eclipse. And it so happened that India had a solar eclipse in 1868. And so Janssen comes all the way from Europe to Guntur, which is in Andhra Pradesh, to Guntur, and makes observations on the solar spectroscope, with his solar spectroscope. And then he finds an additional bright yellow line which didn't match with any spectrum of any known element on Earth. And so therefore, he thinks that this must be a new element. Simultaneously, at about the same time, Norman Lockyer, who was a British, he did the same, but he didn't travel anywhere. He sat at home and did the observations. And he also came up with a new name for that, and he called it as helium. Helios means sun in Greek. So therefore, since it was observed in the solar spectrum, he called it as helium. In fact, there was another person who also played a role in this as far as its terrestrial appearance is concerned. His name is Pommery. He was a volcanologist, and he was studying the emissions, eruptions of the lava from Mount Vesuvius. And so therefore, he found a similar kind of an unknown line in its spectrum. But Ramsay won't give up at that. He actually struggles hard again and then isolates the gas from a mineral which was sent to him by an American friend. The mineral is called clevite, and that he isolates and proves that the so-called D3 line, which occurs at 587.5 nanometers, doesn't is not contained in any element known till then, and so therefore he associates that he had established the spectroscopic method to identify the elements already, right? Kirchhoff's thing had already been put on a very firm footing to identify new elements, and so therefore Ramsay could score very well identifying helium after his achievement with the argon. So look at the kind of achievement that these people had. Ramsay's team. Argon in 1894, helium is 1895. 1 year later, he has two elements already in his kitty. Identifying a new element itself is a very rare event. So therefore, they should actually be celebrating and probably take it easy, be complacent, not work at all, don't do research at all, go home and enjoy kind of thing, attitude they must be having in principle, having identified two new elements. But not for Ramsay and his team. 4 years later, in a matter of 3 months, June 1898 to September 1898, they come up with 3 more new elements which are all belonging to this noble element category: neon, krypton, and xenon. All of them discovered in a matter of 3 months, in a matter of 3-4 months, that they could discover such things. And each of them is a chemically not reacting kind of chemical. And of course, as if out of courtesy, they left the last one in that particular column of noble elements to be discovered by another person called Friedrich Dorn, who did it 2 years later, the discovery of radon. The discovery of each of these elements is not simple. Please remember, all are gases becoming solid, liquid or solid at extremely low temperatures. They are colorless, they are odorless, they are tasteless. These were the methods actually earlier researchers employed in order to identify new elements. In fact, so taste was also one of the important things, and even earlier on people tasted materials and then even paid with their life. They even died because they were tasting some poisons as well. So as well as their atomic. And more importantly, look at their atmospheric content, each of them. Argon forms only 1% of the atmospheric content of air. Helium, 5 parts per million. If you take 1 million air molecules, you will have helium coming up as only in 5 of them. Neon, 18 ppm. Krypton, 1 ppm. Xenon, 90 parts per billion, which means that if you take 1 billion air atoms, you will end up with only 90 of xenon 1. So it was a very tough task for them. And this is where I want us to appreciate the second Indian connection. One of his brightest students who worked on these problems, his name is Morris William Travers. And that's the time, around the time, in fact, 1898, he had completed his PhD working on these different noble gases. And that's when actually the government of India, as well as the Tatas, were wanting to establish a new research institute. And it so happened it came to Bangalore because of suggestions and the philanthropic attitude of the Maharaja of Mysore and all that kind of a story. I won't get into that. So therefore, they were looking for someone who is systematic, meticulous, understands science very well to be heading this new institute. And that's when they write to Professor Ramsay. And Ramsay had no hesitation, without second thought, he said, it must be Morris Travers who should be heading your new institute. And Morris Travers comes to India, establishes the Indian Institute of Science, becoming its founding director. And today you see that it is the most premier research institute in the world, certainly because of the kind of foundation work that Morris Travers had put in. So much so about identifying these new elements. And before I go to the next story, I want to impress upon one particular aspect of all the work that the Ramsay's team had put. Mendeleev had to now accept that these must be belonging to his periodic table. But the whole problem is they didn't have any place where they could place these noble elements which don't react at all. And so therefore, people started doubting the very basis that Mendeleev had used in order to come up with this so-called periodic table. Mendeleev had used atomic weight as the basis for creating the periodic table. So people started doubting it, whether that should be the right kind of basis. That's when actually our next hero in the story comes, who could claim that I laid the basis for the modern periodic table. His full name is Henry Gwen Geoffrey Moseley, or simply Henry Moseley. Henry Moseley enters into the field of research when X-rays and their interaction with matter had just become a very hot topic. This is Henry Moseley. And when he enters, Roentgen had already discovered X-ray. Loewe had come up with the idea of diffraction of X-rays. Bragg and Bragg, Lawrence and William Bragg, the father and son duo, they had come up with the diffraction law, the Bragg, so-called Bragg's law. People are already talking about reflection of X-rays by crystals. And parallelly, two people, especially the latter one, Buckler and Rutherford, was already an established researcher, they had showed that nuclear charge is approximately equal to half the atomic weight of an element. So please remember, atomic weight was still the basis for the arrangement. So Rutherford's observation was quite important to know that the charge now, the nuclear charge, is half of that, approximately half of the atomic weight of the element. Enters another stranger, actually an amateur scientist and a Dutch economist. His name is Broek, and he says, he proposed actually, saying that there must be a new fundamental particle called alphon, and this alphon must be having a charge of +1 and a mass of 2 units. And so therefore, arranging the periodic table should be done not on the basis of the atomic weight, but by alphon, where each element differed from the following one by a +1 charge. And also another point, if I have time, I'm going to talk about, there were anomalies in the description by Mendeleev and his periodic table. The positions of certain elements, argon and krypton, cobalt and nickel, tellurium and iodine, they had some problem called pair reversal. I don't have time to discuss what is pair reversal now. So therefore, people were doubting that atomic weight is not the right one. And that's when Moseley takes much interest in this problem. But pity, he had joined the group of Rutherford for doing research, but Rutherford was not interested in these aspects, but he was more interested in what is contained in an atom rather than worrying about how to put elements on a proper basis. So therefore, Moseley is quite frustrated with the research problem that was given to him. He even writes to his mother on a weekend saying that Professor, that is Professor Rutherford, is more interested in me attending to his automobile. His car had to be repaired quite often. He is more interested in me attending to his car rather than on a research problem that I want to work with. Fortunately for him, Niels Bohr, an established theoretician, already visits Rutherford. And as it happens even today in research labs, this visitor goes around talking to various researchers of what their scientific interest is and whether he could make some suggestions to them. Lo and behold, Moseley says, that's the kind of interest that I have. I don't believe atomic weight to be the basis. I want to put it on a firmer footing. There must be some other parameter that I want to identify that should be the basis for the periodic table. That's when Bohr makes a very important suggestion to Moseley. The degree of scattering of X-rays, that's what his theory says, degree of scattering of X-rays is proportional to the atomic charge rather than the atomic weight. And therefore, he wants this young man to investigate that aspect. And look at the audacity, if you can call it, or the confidence that Mosley had. Mosley says, we shall see. And indeed, he takes up this problem very seriously, constructs a beautiful, very innovative X-ray spectroscope. The spectroscopes that we talked about till now are visible light spectroscopes, but here is an X-ray spectroscope. And I won't go into the detail. Very important, very innovative ideas were put into making this X-ray spectroscopy, especially because those were the days, at least in Rutherford's lab, vacuum or vacuum pumps were a premium, and so therefore he had to come up with beautiful ideas of how not to break vacuum and still analyze a variety of samples. And that's what this picture is about. Sorry, I won't be able to go into the details, but if there is a question, I can describe it. And actually, he's ascribed with the birth of X-ray spectroscopy. So I won't go into the detail, but his contribution is summarized in this graph on the right side. A few months later, after Niels Bohr visit and experiments on 38 different elements, he comes up with this beautiful plot which has a linear correlation between the frequency, the square root of the frequency actually, or in terms of wavelength, you can say, make it square root of the wavelength of the X-rays reflected from a particular element is proportional to Z minus 1, where Z is the charge and the nucleus of the atoms of that particular element. Beautiful correlation between the two. So he not only provided this correlation, he also simultaneously provided atomic number to be treated as a measurable parameter, not treated as a serial number in the Mendeleev's periodic table. It's a measurable parameter, and it can be established from experiment that it beautifully correlates with an experimentally measurable parameter. So he gave it a physical meaning, saying that it is nothing but, what you get is nothing but the number of protons in the nucleus. So this laid the basis for keeping atomic number as the basis for the periodic table and not the atomic weight, as was comprehended by Mendeleev. This is not to undermine the contributions of Mendeleev. Beautiful work. In order, the fact that he could put them in a table itself is a great contribution. But this is how science grows. Nobody is low, nobody is high. Each contribution is put on an analysis that you can do. Except that we can't accept my atomic weight to be the basis. And so therefore, atomic number. Again, another researcher comes to the rescue of the astronomers. As I said, today, X-ray astronomy is a very big subject. They use spectroscopic methods to analyze. For example, this is a supernova remnant, a star which has died. And so therefore, they can look up and find out what are the elements contained in such a distant object. Beautiful kind of analysis can be done. He also solved something that I mentioned earlier, a pair reversal problem. Pity I don't have time to describe what is meant by pair reversal. And so therefore, the position of the elements, he could prove of how to analyze these X-ray spectra that can be obtained by different elements, and then show that they do indeed have an integral step that comes because of the atomic number. This is what I wanted to discuss in detail, but sorry, I won't be able to do justice to Mosley today. The last part about Mosley, before I wind up this story or wind up this talk itself, is about what happened to this man who was a patriot. 1914, Europe was in the holds of a great war, World War I. And so therefore, this man, a scientist, he was not needed to do the job, but he was a patriot. So when my country, when my motherland is at war, I can't be sitting in the lab doing research. I have to be participating. That is the kind of thinking that he had, and that's what he wrote to his mother as well. And then it so happened that he was posted to a place called Gallipoli in Italy, and there he takes a bullet in his head, dies at the very young age of 27. He was all of 27 when he made this beautiful contribution of making atomic number as the basis for the periodic table. And in fact, our condolences should not only go to his family, not only to the country of his origin, but to the entire scientific community. Such a beautiful, such a brilliant young person. Had he survived, probably he would have made more beautiful contributions to science, which all of us would have been benefited. But we can't stop appreciating one simple issue that came out of all these things. His analysis of that there must be atomic number, which is the basis, also created the so-called group 8, which didn't exist in Mendeleev's version, and solved other puzzles in the Mendeleev periodic table. So whatever Ramsay and others had discovered as noble elements, they could find their own column now, which we call as actually group 18 today in the most modern version. It used to be called as group 8. And so therefore, noble gases are all fit into column group 18 today, and because of the contributions made by this young person who died very in tragic circumstances. In fact, if you are interested to read more about Mosley and his contributions, you should pick up this book, For Science, King and Country, The Life and Legacy of Henry Mosley. I can go on like this, but probably I will go to the so-called postscript. I will quickly run through a couple of postscript, which means that the outlook of where we go beyond this kind of thing, of what happened, what are the three stories that I described. Energy dispersive X-ray fluorescence spectroscopy is a big instrument today employed by especially the pharma companies. They can't live without that, the dispersion that is a signature of the kind of elements. And not to talk only of the pharma companies, the entire nanoscience folk, the XAFs is a very important instrument for them to be carrying out very important characterization of the kind of nanoparticles that they would have synthesized in the lab. Without XAFs, it's quite a difficult job to do. So therefore, this is how the spectroscopy has helped a number of fields in science to grow to the level that they have grown today. The last point that I want to mention here with the technical aspect is this particular one. People have discovered till now, as I said, 118 and 119th element is under serious consideration. So a question was posed to Richard Feynman, whose name you would have heard in other context of quantum chromodynamics fame. A beautiful, probably one of the most revered teachers of physics. Richard Feynman was asked this question. Is there an end? Is there the last element that you can ever find? Is there maximum limit fixed for an element to have a particular atomic number? Is there an upper limit? Feynman answers in his own beautiful way, saying that yes, this problem actually should be looked at from a very simple perspective. As the atomic number increases, the speed with which the electrons go around the nucleus also increases. And so therefore, by the time you reach 137, the speed is almost comparable to that of electromagnetic radiation, that is of light. So if you make an element with 138, there is going to be chaos let in, and so therefore that element would not be stable at all. So even if you discover the 138th element, it should be in principle called as imposium, imaginarium, or unobtainium in principle. So therefore, you cannot be having such kind of elements whose atomic number is more than 137. Till now, what I described is something about human efforts in understanding light and the element that the light originates from. But we boast ourselves that we did so much in science and etc. But every time you look at this problem from a philosophical aspect, you should appreciate that nature has already done what we did in the lab. And here is a video. I hope that you can listen to the audio as well. If not, please stop me. I will probably try to see how I can help you doing that. And here is a very short clip of about 2 minutes. I will run that clip now. Can you, sorry, did you get the audio? Can somebody
Please
confirm?
try to share once again, sir. Play it once again.
Okay.
No audio, sir. No audio, sir.
Audible?
No, not audible, sir.
I don't know how to do that. Ah.
Sir, share. After sharing, you please select share with computer audio.
Okay. How do I do that? You have to guide me with that.
Yes.
I go back to this one. WebEx events. No.
The video is in the presentation itself, sir.
Yeah. So what do I do? I don't get any icons here. Oh, so sorry about that. No, I don't see any kind of icons which can help me doing that.
Sir, separate video is there. If it is there, we can share it separately.
Oh, goodness gracious. Oh, I'm so sorry. This was about Northern Lights because there is not much text. You have to watch the video to appreciate it. So therefore, I'm sorry you won't be able to watch that. This was about, probably I'll read it out as it says. The gaseous particles that are present in the atmosphere and how light actually gets emitted from the two poles is what, if you have watched a movie called McKenna's Gold, that's where actually this is very well depicted. If you go to the poles, and if you are lucky on that particular day, you would be able to see this beautiful light that's being displayed on the sky. And each of those lights, each of the colors there represents a particular element. And from the color that is emitting, you can make out what's the kind of color that you have. That's what this video and the audio that goes with it. I'm so sorry you were not able to hear the audio, and I don't know how to get this to work. Okay, with that, I would
read it
like.
out, sir. Thank you,
Sorry.
sir. We were
Sorry?
unable to hear the audio, but you read it for us, so, sir. Thank you, sir. We came
Yeah.
to know with the video.
Yeah, but I don't think I did a proper justice to this one. Anyway, thank you very much. I want to stop here, and thanks for participating in this program. And thanks for the opportunity, especially.
Thank you very much, sir. Such a wonderful presentation. Now I request audience, if there are any questions, they can post in the chat box, or they can mention in the Q&A. Or if there are no questions as of now, you can contact us later also, so that we can get back to you and clear your doubts or any clarifications on your queries. So in the chat box as of now, there are no questions.
Okay.
I request audience, if any queries, now there is a chance to speak with sir directly. You can raise your virtual hand so that I can unmute you and you can speak to sir. If there are no questions, we will wind it up formally. Thank you very much, sir, once again.
Thank you.
I request audience to please try to ask the questions. If not now, later, at least.
You can send me a mail if you are so interested. We can always correspond. So therefore, it should be possible.
And I request all the audience to, sir has mentioned one book on Mosley. You can purchase it and you can go through that completely, which will be helpful for you to increase your scientific temperament. Thank you very much, sir. Now, on behalf of KSTA and on behalf of all the teachers and my own behalf and all the students, I would like to thank you very much, sir, once again for delivering today's session.
Thank you.
Also, I would like to thank our chairman, Professor S. Ayappan, sir, our CEO, Dr. M. Ramesh, sir, and other senior scientific officers, and technical and non-technical team, Sri Siddhegoda, Mr. Anthony Lobo, and other colleagues who are working behind this program. And last but not least, I would like to thank all the teachers and students who have joined with us, though few in number in WebEx, but the larger audience in YouTube, and the more audience will be watching later in YouTube, sir. To all those, I would like to thank you on behalf of KST and my own behalf. Thank you once again. Thank you very much, sir.
Thank you, Dr. Umesh. Thank you very much.
Thank you.
I'll sign off now.
Sure, sir. Thank you, sir. The answers will be sent to you, sir. The students who will be answering your questions,
Okay.
they will be sent to you, sir. The best answers will be chosen by you, and we will be
Okay.
giving them our.
Pleasure.
Yes, sir. Thank you.
Pleasure. Okay. Bye.
Bye, sir. Thank you, sir.